Hi there, welcome to my video. In this video, I'll explain my project which I did in order to learn how to apply linear regression and how to check the assumptions for it. So let's dive right into the project. Yeah, so this project involves a data set which is from a company which helps students get admission in universities abroad for the graduate purposes for master programs. So this data set is from that company, and the problem statement we have is analysis is to be done which will help the company in understanding what factors are important in graduate admissions and how these factors are interrelated among themselves. It will also help predict one's chances of admission given the rest of variables. So let's have a brief look at columns in our data. So it's pretty simple. We have a serial number which is showing the unique row ID. We have GRE scores, we have TOEFL scores, we have university rating, that is the rating given by the company's team on the university that the student attended for their undergraduate. We have rating for a statement of purpose and letter of recommendation. We have undergraduate GPA. We have research experience, which is either 0 or 1. And we have chance of admit, which is our target variable. Right. So this is the brief look at our data. We have 9 columns and 500 rows. So this is the basic information. We almost all the columns, all the columns are integers or floats. This is the using describe function. These are the percentiles of each row, of each column. We have maximum and minimum values also. Now let's check for missing values. So as we can see, we were lucky. There were no missing values in the data. For unique values, serial number is 500 unique because it represents each row. We have 500 rows. For GRE score is 49, TOEFL 29, university rating 5. So it would be like 1, 2, 3, 4, 5, 1, 2, 3, 4, or 5. SOP is 9 and LOR is 9. So as we can see, the unique values of SOP and LOR 1, 1.5, 2, 2.5 until 5. So we have 9 values similar in for LOR. For CGPA, we have 184 values, research 2, which is either 0 or 1, chance of admit 60. So this is the overview of our data. Now let's deal with outliers first. So this is the function I have written. It simply, for all columns, it computes the IQR values. And using that, we just compute lower bound, upper bound. We compare each row, we compare value of each row with this lower bound and upper bound, and if it's greater than or lower than upper bound of that, we consider it as outliers. So we are just counting for now how many outliers we have for each column of our data frame. Yeah, so here is the result. For chance of admit, we have only 2 outliers. For LOR, we have only 1 outlier. So as we can see, number of outliers are very less. So we'll simply remove them. This is a function to replace outliers with none. And after we replace it with none, we'll simply remove using drop NF function. So yeah, this is our, as you can see, there are 0 NaN values, hence 0 outliers in our data. Now let's move forward. This is the shape after removing, obviously. Um, yeah, so we are here removing serial number because it's not at all useful for us. It's just showing the unique row number. It's not useful, so we will remove the serial number column. And here we are plotting the correlation heat map. Yeah, so as you can see, the TOEFL score, the TOEFL score, the GRE score, and the CGPA are highly correlated with each other. So, and this columns are also correlated highly with the chance of admit column, as you can see, CGPA, TOEFL score, and GRE score. But for now, we will not remove these columns because we, after training, we will check how it is affecting our target variable. So after training, we'll decide if we want to remove this column or not. For now, we'll keep them even if they are correlated, right? So let's start with the univariate analysis. Univariate analysis we will do for each column. So this is for, we are just plotting his plot with KDE. For GRE score, we can see it's like almost Gaussian shape. For TOEFL score, it is like similar to Gaussian. For CGPA, also it's similar to that of a Gaussian distribution. Now this is for our university rating. We can see 3 has the maximum number of counts for university rating, and one is the least. SOP, we have 4 and 3.5 as the highest, and 3, then 4.5, and the lowest is 1, as you can see. Right. So this seems to be perfectly Gaussian distributions. Now, this is his plot for SOP values. Here also, we can see it's similar to the shape of Gaussian. For this is KDE plot for SOP column. This was his plot, but this is KDE plot for SOP. So as we can see, the distribution is that similar, very similar to that of Gaussian. Yeah, this is for research values. We have more people in our data set that have research experience in comparison to that students who does not have any. Now, this is frequency plot for LOR. As you can see, 3 has the most, 1.5 is the lowest, right? So this is the distribution with KDE, and as you can see, it's like similar to Gaussian for KDE plot. For LOR, it's you can see similar to Gaussian. This is KDE plot for chance of admit. Again, looks similar, not exact, but similar to the Gaussian. Let's start our bivariate analysis. So we have doing bivariate analysis of uh, SOP, LOR research and university rating with chance of admit column, which is our target variable. So as we can see, this is for SOP and chance of admit. It shows for one, the distribution is like a small this thing, and we can see it's the 50 percentile would be around 0.55 or around 0.6, right? And similarly, as we increase the SOP, the 50 percentile, which is for each of the SOP values, is increasing, as you can see. And similar is for LOR also. You can see this increasing trend in values of increasing chance of admit, the median values, with increasing the values of LOR. And for research also, the uh, median and the most distribution of that is around between 0.6 to 0.7. For people who have no research experience, for people who have research experience, is higher than that of chance of admit. Median is higher than that of uh, people with no experience. For chance of admit versus university rating, you can see that as rating improves, the chance of admit median value also improves. So yeah. Now let's also see for our numerical columns such as GRE score, TOEFL score, and CGPA with chance of admit. As we can see, this shows correlation with chance of admit, and as we also have seen this in the graph correlation chart, that all these columns, GRE score, TOEFL score, and CGPA, has positive high correlation with chance of admit. We can also see this from this graph, right? So yeah, our variables are, our features are good. Checking for duplicate, this is just to check if there are any duplicate values or not. There are none. And now let's start our data pre-processing. So we'll use normalization for pre-processing our data. Normalization will bring all the values in between 0 to 1 for all our features, right? So we have just used min scalar from scalar, transform our data, and this is our transform data. Now, this is again checking for missing values, none. So let's go ahead and split our data into train and test using train test split. We split the data. Test size is 0.2, means 20% of data is for training, sorry, for testing, and 80% of data is for training. Right? Sorry. Now, this is the view of our X train. So it's 397 rows and 7 columns. And this is our X test, 100 rows and 7 columns. Right. Now we'll apply 3 models of linear regression. One is vanilla linear regression. One is lasso with alpha value 0.001, 0001, and alpha for ridge. The alpha value we have set is 0.01. Now we'll see the mean R square value of all 3 of them. So as you can see, it looks similar. All of 3 look similar, 0.638 approx. So we'll go ahead with just vanilla linear regression, but we want more details of our results. So we'll apply linear regression, but with stats model library. As we know, stats model does not add the constant value by itself, so we have to add it manually before training. So we have just used add constant function, which adds the intercept column to our extreme data. Now after adding that, we are training our ordinal. We are training our just a second. Yeah, ordinally release squares method. This is the name of method that is there for linear regression in stats model. So we are training our ordinal least squares method, uh, and these are our results. So we have just used the summary function on the results object that we have right after fitting the data, and here we get our regression results. And as we can see, these two values are important. R squared is 0.83, and just that R squared is 0.82, which is quite good. And other important values are coefficients. So as we can see, these are the coefficient values, means the parameters for each of our columns. And this is the p-value, which shows the effect of each of these variables features on our target variable. So now let's have a look at this. As we can see, the lowest value is of research, which is 0.01. But should we simply remove this because it has low value? No. We also have to check for the p-value, and it shows that the p-value is 0.022, which is less than 0.05. So it is lower than our significance value. That means alternate hypothesis will be true. So what is our null and alternate in this case? The null hypothesis is that this feature, which is research, has no effect on our target variable. And our alternate hypothesis is the feature research has effect on our target variable. So this shows that our alternate hypothesis is true. That's why we can't remove the research column, right? So what is the next lowest? I think this is the next lowest. Yes, this is the next lowest university rating. And if we see the p-value is higher than 0.05, which means null hypothesis is true, and which means it has no effect on our target variable. So we'll just remove the university rating column, and using drop function, we remove the university rating column. Now let's again train our model and see the summary of results. We can see there was not much effect on our R square and R square adjusted. It's almost similar, but we were able to reduce one feature. Okay, so yeah, yeah. So let's have a look again. Mm, yeah, so here I have also written the insight that features with highest weights, which is highest coefficient value, are GI score, CGPA, and yeah, so this both are the most important in this case, right? Because yeah, and so these are the most, and their p values are also almost zero, so which means that it is also affecting our target value, right? So yeah, so let us check for least values, which is the least. Yeah, I think SOP is the least, right? 0.05, but the p value is 0.05. So we can't remove this feature, and we can see all the features has p values less than 0.05. So this means all these variables have effect on our target variable. So we can't remove this features. We have to keep all of them. Yeah, so this is right. Now another important aspect when training linear regression is the checking of assumptions. So generally there are 6 assumptions. First is no outliers, which is we have satisfied that assumption because we have already removed outliers. Second, linear relationship should exist between feature and target variable, which we already saw. The third should be no multicollinearity. I'll explain this in a bit. Normality of residuals, no heteroscedasticity, no autocorrelation. So the sixth one is here autocorrelation means the degree of correlation of variables value over time. So this is the autocorrelation is involved in mostly time series data. Like for example, data involving data of stock market, price of stock over the period of time. So that means the values of previous rows is uh, having effect on the values of later rows, which means it's dependent on time. But in our case, that is not true. So this assumption for us is also satisfied. So let's check these three, which are important. There should be no multicollinearity in data. So let me explain multicollinearity. in simple language, multicollinearity means any independent variable should not be the result of linear combination of other independent variables. That means that suppose A is multicollinear to B and C. That means A can be written as alpha times B plus beta times C plus some constant values, right? So if this is the case, then A is multicollinear B and C, right? So we have to remove all the multicollinearity from our data. So let's check if there are multicollinear features in our data set or not. We'll do this using VIF, right? Various inflation factor, which is taken from stats models library. Now, there is a simple process to remove multicollinear features. So what is the process? It is simple. First, you have to add the constant into which is already added in our case, and we have to check the various inflation values, VIF values, for all the features that we can see here. Now, for features which has VIF values more than 5, we have to remove that feature, and then we have to check the R square value again after removing that feature. So if the R square value falls below the threshold is generally 0.8 to 0.85, right? So in our case, let's assume it to be 0.8, right? So if our R square value is less than 0.8 after removing a feature, we will not remove that feature, we'll keep that feature, we'll move to other feature which has high VIF value, means VIF value higher than 5. But in our case, we are lucky that the VF values we have are of these features is all less than 5. We have to not we have to ignore this constant. So let's this means that we do not have any multicollinearity in our data. Yeah, so third assumption of our is also satisfied. Now let's move to the fourth, which is normality of residuals. So it's simple. There are Q2 plot tests which we can do. This is a visual test to see if our data is normal or not. Our residual values, which means the error values, are normal or not. So as we can see, it seems almost fitting the line, but we are not sure. So we'll just do a plotting of this residual values using this plot. We can see that it's normal, but let's see by finding out the mean of this distribution. So it comes out to be 0, which satisfy the mean of residuals assumption of ours, and we to again confirm it, double check, we also will use Shapiro test, which is showing that our p value is 0.93, which is greater than 0.05. So our null hypothesis is true. We cannot reject the null hypothesis, which is that our distribution of residuals is normal. For more double checking, we have also used KS test, which is generally good, more reliable than Shapiro if we have n greater than 50. So KS test is also showing similar results, greater than 0.05 p value. So null hypothesis cannot be rejected, which means that our distribution of residuals is normal, which satisfies our assumption. Now let's check just a second. Yeah. So the next assumption we have to check is no heteroscedasticity. So what is heteroscedasticity? Heteroscedasticity means that there is high variance for my residual values when the value of x-axis, which is the fitted values, increases, right? So the variance should be same for residual values, and if this is the case, it is called homoscedasticity, which we want. We don't want the heteroscedasticity, which means we do not want high variance for our residual values. So this is the visual way. We have used scatter plot to plot residual values versus fitted values, but visually it's not that clear. It seems like there is change in variance for residual values, but it's not that clear. So we'll use some test. The test for this is Goldfeld want test for homoscedasticity. And as you can see, p value is greater than 0.05, which means null hypothesis cannot be rejected, which means there is no heteroscedasticity. We satisfied our that assumption also. So hence all our assumptions are satisfied. We can say that this model is good in that case. Right? Now, another important thing for having insights is the graph of ypred versus ytest. So we want to see how our ypred is behaving, values of ypred is behaving in comparison to the actual values, which is the ytest values, right, which we have provided. So we simply plot the graph between them. There is an interesting pattern here which we can see if you draw a line here and between 0 in 0.7, suppose if you draw a line here, you can see the data over here is increasing proportionately with increase in y-test values. Y-pred is also increasing proportionately. But before this line, before the value of 0.7 for y-test, the y-pred value here, if you can see my cursor, this values is not increasing proportionately with increase. Like for example, consider this point. This point has increased this y-test value. So actual value is between like 0.4 to 0.5. Consider 0.5, but the y-pred values has increased very low. It's not y-test value has not increased as much as y-pred value has not increased as much as the actual value is telling. So there is a problem in this case, which is showing that our model has underfitted. Our model has high bias in this case. So important insights: when my chances of admit is higher than 0.7, the model is giving good prediction. But for y-test value less than 0.7, model predictions are not good at all. So what are the recommendations? Like I said, it has higher bias, underfitted model. So what can we do? What are some suggestions to fix this problem? So simple thing is we need to bring more complexity into our model, right? So how can we do that? One of the way is get more training data when chances of admit are low, because it is when the chances are admit are low, the model is having problematic prediction. One way is this. We can increase more features to identify the chances when the actual values are low. So this might help. And like last I suggested, increase complexity of model by maybe trying polynomial regression, which is more complex than linear regression. So these things might help improve our model more. So as you can see, this graph is very powerful because it gave us a lot of insights into how we can improve uh, uh, this particular model in this case, right? So yeah, that's it. Thank you for tuning in. I hope you understood my project. Thank you.